Okay, so I plugged this into Google Sheets, and I got the same exact graph that I have over here. Let me label my axes though. So I have the same graph that they gave me. And now what I want to do is I said, oh, if I graph distance versus time squared, I'll get a linear relationship. So let's do that. So my distance will be the same. And then instead of time, I want to graph time squared. And that is in seconds squared. So that is my unit for time squared. A little bit of an awkward unit, but that's okay. And what I want to say then is this squared, and drag that down. And now I have my time squared values. So then I want to insert a chart. Not that kind of chart. Come on, Google Sheets. Why do you do me like that? Oh my gosh. Insert chart. Okay, one sec. Okay, so I just created a new sheet in here because this thing was not behaving. So I graphed my new data points and I put in a line of best fit, and I see, well, hey, this is pretty dang linear. And it gave me a line of best fit of 4.99x plus some really small value. So we're just going to say that we do not have a vertical axis intercept. So really quick. Right, sorry, I thought there was a way to force it through 0, 0, but that's okay. So yeah, so we have a line of best fit. We're just going to ignore our vertical axis intercept, our y-intercept, just because we didn't have one before. We saw that at time 0, we were at 0 position. That's what we had before. So we're just going to roll through and say, we don't have one. So we have a line of best fit of distance equals 4.99 t squared. So let's come over here and say, okay, well, we have d equals 4.99 capital T, which was d equals 4.99 t squared. So that's our line of best fit. We would input our graph in there, and we'd be good to go. So it says, using the slope of your graph in part C, calculate the acceleration g due to gravity in this experiment. So this gets a little bit tricky, but what we can do is we can use our equation that's y equals y naught plus v naught t plus 1/2 a t squared to help us out. So we know that this is a case where we have something falling some sort of distance over some amount of time. We have time values, we have distance values, and we want to know the acceleration. So what I can say is I can start taking this equation and I can start matching it up with the things that I know, or with the equations that I have. So I can say, well, in this case, if we go up here, it looks like our y naught, if I'm just kind of making a list of what I know, looks like y naught is equal to d. It looks like I'm starting at some distance d off the ground, and my final height, this y, is just equal to 0, because I end up at 0. It also looks like, because I'm just being dropped, my v naught in the y direction is also just 0, so that's really helpful. And then I don't have anything pushing it down except for gravity, so I'm going to say my acceleration is negative g due to this gravitational downwards pull. So it's accelerating downwards based on g in this negative direction. So this is what I know. Let me try to bring this all down. So that's me just analyzing the situation, thinking about what I know. And I can start to plug this into my equation. So let's do that. So we say y is equal to 0, y naught is equal to d, v naught is equal to 0, minus 1/2 g t squared. So I said, hey, the acceleration is negative g, so I just kind of put the negative out there. So I can move this around and say 1/2 g t squared is equal to d. And then I can make this look like my equation that I made up here based on my line of best fit. So d is equal to 1/2 g t squared. So we can compare it to what we found when we linearized our data. Our data told us that d is equal to 4.99 t squared. If we compare these, it looks like our slope, 4.99, is 1/2 g. So look like 1/2 g is equal to 4.99. Okay, because this was t squared, so this is what we have. That's t squared. This is d, and that's d. So really our slope then has to equal this missing piece, this 4.99. So if we want to solve for g, we can see j is equal to 4.99 times 2, which is something I should be able to do in my head. But alas, 4.99, let's do 9.98. And that's how we do it. So that's kind of an example of how linearizing our data can actually really help us in a situation like this. So what we're going to do tomorrow is we're going to do an experimental design type question, and then that will lead us back to this question of how can we use, let me see if I can find it again, how can we use this linear graph that I showed earlier, how can we use this linear graph to help us figure out that question about the archer? So we want to know, hey, what height is the archer, the perfect height of an archer, so that they can just shoot horizontally, so that they hit a bullseye without really aiming up or down if there's no wind. So we're going to be able to use this linear graph to help us out with that tomorrow. But so yeah, that's what we are looking at today. And yeah,